Hello, hi student. Good evening. So today we are going to start one new topic that is about concept of whole. Okay. So let us see concept of whole in valence band. Okay. So concept of whole. Concept concept of whole. Whole. Okay. So today we are going to discuss this topic. Okay. So now see. As in last class we have seen what about effective mass of electron in conduction band. Okay, so now today we will see the concept of hole. Okay, after this we will see the effective mass of hole in valence band. Okay, so conduction band we have seen. First we will discuss about this topic. Okay, now after that we will go further. Okay, so now see what do you mean by this hole? What is hole? What is hole? See, actually, as we have seen in last lecture, that a two-dimensional representation of covalent bond. Yes, two-dimensional representation of covalent bond. When we see for the silicon crystal under 0 degree Kelvin, then that time you see here the silicon atoms. Let us say I am taking 4 silicon atom for our convenient purpose. Okay, so this is my silicon atom, and these silicon atom are what surrounded by valence electron. How many valence electron? How many? 8 valence electron. Okay, so each silicon atom are surrounded by each valence electron. Okay, so these are my valence electron. Okay, this is actually what mutual sharing of electron between each silicon atom. Okay, so actually outermost shell of silicon atom, they have 4 electron. Okay, so when they are coming closer to each other, they will share the electron. Okay, one and each other. Okay, so that is covalent bond. Covalent bond is nothing but mutual sharing of electron. Okay, so let us say this is under what 0 degree Kelvin. Means in this case what this solid or crystal is what neutral. Okay, under 0 degree Kelvin, because nothing is free, no particle is able to move here, so therefore there is no conduction, nothing is going on. So under 0 degree Kelvin, so it is electrically neutral. Okay, so now what we will do, let us take this system or the crystal in where some place where the temperature is greater than 0 degree Kelvin. So actually the normal temperature of room temperature like 25 degrees Celsius to 27 degrees Celsius. If we will take this to room temperature, then what happen? Then the valence electron, which are participating in the covalent bond, okay, will gain some thermal energy. Okay, so then they will break this covalent bond and will come out of this bound state and jump into the conduction band. Means here conduction band means what? Interatomic space. Okay, interatomic space. Now here at the same time there is a positively charged empty state that will create it inside what crystal, means in valence band. Okay, so in valence band representation means outermost shell. How many electrons are there in outermost shell of electron? These are represented in what valence band. Okay, so in valence band, see here, as temperature increases, let us say this is now T not equal to 0, means T is greater than 0 degree Kelvin. So that time this electron will get energy, thermal energy, and will jump to the conduction band or in interatomic space inside the crystal. Okay, so then there is a positively charged empty state that will create it. Okay, so now this electron will jump to this what empty state. Okay, so it will replace this empty state. Now here positively charged empty state will get created. Now further this electron will come and this electron will come. Okay, so this will fill this positively charged empty state. Okay, so then whole or positively charged empty state will get created here. Okay, so then this electron will jump here, okay, and replace this hole with electron. Okay, so then here what positively charged empty state will get created. That is what, okay, we are observing like that the hole is moving. What hole is moving? Okay, so let us see here. Let us take three electron. Okay, so through this we can understand very well. Okay, so these are electron, where in valence band, okay. So when temperature is greater than 0 degree Kelvin, then what happens? This electron will jump to conduction band. This electron will jump to conduction band. Okay. So now this here positively charged empty state will get created. Positively charged empty state will get created. Now this electron will jump. Now this electron will jump to this positively charged empty state and it will replace this by electron. Okay. So this by electron. Now here what? Now here positively charged empty state will get created. Okay. So now this electron will come and it will jump. Okay. So now it will replace this. It will replace this positively charged empty state. Okay. Positively charged empty state. Now see here. Now see what we are observing here. This electron movement. Okay. This electron movement when temperature is greater than 0 degree Kelvin, this electron will jump to the conduction band or in interatomic space. Then what happens? This electron will replace this positively charged empty state. Now here the electron in valence band under the temperature greater than 0 degree Kelvin. So the electron in the valence band, which are nothing but bound electron, they will move from one bound state to other bound state. So therefore the movement of electron, they will alternatively what they will alternatively fill one empty state and create the new empty state. Okay, so now see here. Now here is electron. Now here electron. Now here this has jumped that side, so therefore there is a creation of positively charged empty state. Okay, so now what is there? The motion. So this overall motions of this electron, which is bound electron, okay, bound electron from one empty state to another empty state, is equivalent to the motion of what? Equivalent to the motion of this what? Positively charged empty state. Positively charged empty state. So therefore from here what we can say that the crystal that is available to us has the second important charge carrier, which is responsible for what? Current. Okay, here in valence band, which one is moving? Hole or electron? Hole is moving. Electron is not moving. Actually, electron is moving, but in a real case, actually electron is moving, but we are observing like that. But it is seem like that that positively charged empty state is moving, but actually electron is moving. Okay, so this is best for this to understand. So one of the best analogy is that what? Take one water bottle. Okay, so this is my water bottle. See here, this is my water bottle. Okay, let us see. This is my water bottle, which is filled with water, almost full, but there is, okay, so almost full, not completely full. This is almost full with water. Okay, this is almost full with water. Okay, so this is my water bottle, which is filled with water. Okay, almost filled with water, but not completely filled with water. So now here at this neck of this what neck of this water bottle, there is a small bubble. Okay, small bubble. Okay, I think you might have seen this small bubble when you fill the water bottle full. Okay, almost full, then there is what? At the neck there is a some bubble, one two bubble. Let us say for understanding purpose, there is a small bubble. Okay, small what? Bubble. Okay, so this is my water bottle. This is my what? Water bottle. Now when we tilt this water bottle, then what happen? Let us say I am tilting this water bottle here. Okay, so I am trying to tilt this water bottle like this. Okay, like this. Let us tilt this water bottle like this. Okay, so in this time when I am tilting this water bottle at some angle. Okay, so then this bubble will come where? Here. Okay, so this bubble will come here. Okay, so now then again you tilt this water bottle again again tilt this water bottle almost horizontal, but greater than slightly horizontal. Okay, so this much. Okay, I am tilting this water bottle almost like this. Okay, so this. Now see this one. Okay, so this is my water bottle, same water bottle, same water bottle. Okay, so now see this bubble will come somewhat at corner side, at this place. Okay, this place. So water bottle is that what, water bubble is this. Okay, this, when you will tilt this bottle, water bottle like this. Okay, so this is my water, this is my water inside the bottle. Okay, so this is water, this is water. Okay, if you will see here in first case, when the water, when the bottle is perpendicular, just bottle is placed here. Okay, so that time the bubble is here. When you will tilt this slightly, then that time the water bubble is here. Okay, when you will tilt this when you will tilt this water bottle almost horizontal but not perfectly horizontal, that time this, what this water bubble is here. Okay, so see the position of water bubble, it's here, then here, then here. Okay, so what is actually what we are seeing, that we are able to see that this hole, this water bubble is moving. This water bubble is nothing but our hole. Okay, so this is what hole, hole. This is hole, and this water is what? This water is nothing but our electron. Okay, electron is water. Okay, water, and this hole is nothing but water bubble. Hole is nothing but water bubble. Okay, so this is my water bubble. This is my water bubble. Okay, hole is my water bubble. Okay, water bubble. This is my water bubble. Water bubble. Okay, so now see here, electron is my, electron is what, electron is corresponding to water. Okay, related to water, and this hole is related to water, water bubble. Okay, water bubble. As you are tilting this bottle, this water bottle, this hole is moving, this hole is moving like this. Okay, like this. What exactly is moving? Exactly, this water bubble is not moving, but actually the water is moving. Actually, what water is moving, water is moving. Why? Because here water, here if you see, because here water that is related to electron are in majority charge. Okay, are in majority, are in majority. Okay, so these are in majority. Okay, so here water bubble, if you see this water bubble, this is my water bubble, that is related to what, hole. Okay, hole, which are in minority. So these are in minority. Okay, so these are in minority. Similar cases here. So this is the analogy to understand what this movement of positively charged empty state. Okay, so actually in case of bottle, I also say this water is what, this water is nothing but electron. Okay, which are in majority charge carrier, which are in majority charge carrier. When you will tilt this water bottle slightly. Okay, when you start slightly tilting this, and then you will see what, you will see what, the water bubble is moving, water bubble is moving, but actually what is moving? Actually water is moving, water is moving. Okay, so why? Because why it is seen like that? Because the water bubble are in minority, water bubble are present in minority. Okay, so whereas the water is present in majority. Wherever we see the majority, that we will feel like that they are in rest, but actually they are moving. Okay, here water is moving because it is in majority. Okay, here water bubble is what, water bubble is at rest, but it is not moving, but it is looking like the water bubble is moving, because they are in minority, they are in minority. Okay, so their concentration is minority, water concentration is majority. Okay, so this is only the analogy to understand this what concept of hole. Similarly here, what the electron movement of electron, they are alternatively filling what positively charged empty state, and alternatively creating new empty state. Okay, alternatively filling one empty state and creating new empty state. So therefore the motion of this electron in the valence band, which are nothing but bound electron from one bound state to other bound state, are looking like what? So this motion is nothing but this is almost equal to the moment of positively charged empty state. Positively charged empty state. So therefore this positively charged empty state movement of this will give rise to what? Current. So therefore the crystal which is available to us has second important charge carrier like electron charge carrier, which is responsible for what? Current. And this charge particle is nothing but is called as what? Hole. That is called as hole. So this is the basic concept of what? Hole. How actually the hole? What is hole? Hole is nothing but it is just a positively charged empty state. Okay, so which is what? Which is moving in the valence band. Okay, which is moving in the valence band with the help of movement of what? Movement of electron, which is bound electron from one bound state to other bound state. If we see in reality, this hole is not moving at all, but because they are in minority charge carrier, so that it is looking like that the positively charged empty state are moving. So therefore the current at therefore here current in the valence band is due to this hole. Okay, so which is just nothing but the moment of positively charged empty state. So hole is nothing but these are positively charged empty state. Okay, positively charged empty state which is moving in valence band. Okay, so to understand that, the analogy is this water bottle analogy. Okay, so this is about what? Hole. Okay, so therefore the crystal has second what? Important charge carrier. Okay, so that is nothing but hole, which is responsible for current. Okay, so this charge carrier can be thought as a classical particle. Classical particle in the sense means big. Okay, at big scale. Okay, whose motion can be modeled by Newtonian mechanics. So now see here the current in the current due to the electron in valence band. So that is what the current, drift current density. See here, drift current drift current density drift current density drift current density due to what? Due to electron in where? In valence band. Drift current density drift current density due to electron in valence band is given as valence band is JD is equal to minus summation this minus charge, okay, electron, minus E summation I filled into Vi. Okay, so this is my drift current density due to the electron in the valence band. Okay, in valence band, and this summation is what? Extended in overall full of band. Okay, overall valence band. So overall valence band, and it is somewhat inconvenient because it take into account all the energy state. Okay, so let us puts all the energy state. So therefore, if we see here, the total drift current density due to both electron and hole is nothing but JD is equal to this is minus E summation I total Vi plus E summation I empty Vi. Okay, so this is what total drift current density. Total drift current density. I total due to movement of electron in both valence band and conduction band. Okay, so but the electron will give rise to current only when it is in conduction band, because in conduction band there is a free electron. Okay, so movement of electron in the conduction band will give rise to what? Current. And this is empty state means what? These are electrons in the valence band. These are bound electron moving from one bound state to other bound state, means it is the actually the movement of what? Hole, means positively charged empty state. Okay, so this is what? Total drift current density. Now if we say that, if we say what? If we say for example, if we say, let us assume that if the valence band is completely full of what? Completely full of electron. If the valence band is completely full of electron, Okay, so then is there current due to electron? The current due to electron is what? Almost zero, means completely zero. So therefore there is no current due to electron if the valence band is completely full of electron. If if the if the valence band is completely, if the valence band is completely full of electron, then this implies that this implies that the current due to electron is what? This I total into Vi is equal to what? Zero. This current will become zero, and this implies that we are left with what? Drift current density is only due to what? Hole. Hole has charge plus C summation I empty into Vi. So now we are left with this one, this current. So this is the drift current density due to what? Hole. Due to hole. So now see here the indication of this current density. This drift current density is very important. What it indicate? Let us see. So this is drift current density due to electron in the valence band. Okay, electron in the valence band in the sense that the drift current density due to what? Due to hole. Okay, ultimately we can say that drift current density due to hole, or you can say the drift current density due to electron in the valence band, means these electrons are bound electron moving from one bound state to another bound state, which implies that moment of a hole. Exactly, the moment of hole will give rise to what? Drift current density. Okay, in valence band. So therefore, let us see this. Okay, note it down. So then we will see the consequence of this, and the what exactly it is indicating. Okay, so drift current. So when valence band is almost what? Full of electron. Almost full of electrons means there is no free electron in the conduction band. So current due to electron is what? Zero. Okay, so let us see here. Now the indication of the drift current density due to hole that we got is what? So this is JD is equal to what? Plus C summation I empty I empty into Vi. Okay, so this is my drift current density. So now see here. Now see this Vi is a function of E, which is nothing but 1 by h cut dE by dk d by dt. Okay, so this is what Vi is the velocity of what? Particle. Velocity of particle, which is the function of energy, is equal to 1 by h cut d by dk. So that we have seen in the last class. Okay, in case of what? In case of effective mass. In case of effective mass, that we have seen. Okay, this one. Okay, so now here this is what? Velocity of particle. Okay, so now it indicate what? It indicate that how well the positively charged particle. Okay, how well the positively charged particle move inside a crystal. Okay, so this is what indication of this Vi is the velocity of particle, which indicate that how well the positively charged particle move inside the crystal. Okay, so now this total equation represent what? This indicate the indication of this is that the positively charged particle replace all empty state. Okay, so all empty state, the positively what? Charged particle is placed in empty state. Okay, so this indicate that what? Positively charged positively charged particle positively charged particle positively charged particle placed placed in placed in what? Empty state. Empty state by assuming by assuming all other, by assuming what? By assuming all other state as empty, as empty, or neutral. Okay, so this is what the positively charged. This indicate what? This indicate positively positively charged particle placed in empty state by assuming all the other state as empty, okay, or neutral, okay, or neutral. So this is what we can show this by what? EK diagram. So this is what this see here. So this is my EK diagram for what? Valence band. Okay, this is E versus K diagram. Okay, so now see here. What this indicate? This indicate that the positively charged particle. So assume that there is a some hole is present here. Empty, not hole. Some empty state is present here. Some empty state is present here. Okay, near the top of valence band. Near the top of valence band, some empty state are present. Okay, so these all the state are replaced by what? Positively charged empty state. Positively charged empty state. These all state are replaced by positively charged empty state, and all the other state are assumed as empty state. All other state are assumed as empty state. Okay, so all the other state are assumed as empty state. Okay, so this is the indication of this means this is the new concept. What? This is the new concept of what? Hole through the energy versus K diagram. Energy versus K diagram. Okay, so now when we saw what? Total drift current, that is due to both electron and hole. But after that we assume that the valence band is completely full of electron. Completely full of electron. Okay. So therefore there what? The current due to electron is what? Zero. The current due to electron is zero, and the current that we have left, that is only due to what? Hole. Due to hole, positively charged empty state. So this is what? This current, this drift current, here which will replace what? Which will drift current. This drift current indicate what? The movement of positively charged empty state, positively charged particle. Okay, positively charged particle. Okay, so these positively charged particle will what? Will replace or placed in what? Empty state. Placed in empty state by assuming that there is some empty state which is available at at the top, at near the top of the valence band. Near the top of the valence band, by assuming that there is some empty state. Okay, so all these empty state is replaced by what? Positively charged positively charged particle. Okay, positively charged particle, and by assuming that all the other state are empty or neutral, electrically neutral or empty. Okay, so this is the concept of, this is what? New concept of hole. Okay, or you can say this what? This is new concept. This is new concept of hole. This is new concept of what? Hole. New concept of hole or positively charged empty state. You can write like this also. New concept of positively charged positively charged charged positively charged empty positively charged particle positively charged particle occupying 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 the what? Original empty state. Original empty state. Okay, so this is the indication of this. Okay, so this diagram, energy versus K diagram, EK diagram. Okay, so here K is what? Momentum, which is not directly momentum, but it is related to momentum for free particle, which is nothing but P by h cut. P by h cut. Okay, so as we know, P is equal to h cut K. H cut K. and this k is nothing but it is a wave propagation vector. Wave propagation vector. Okay. So this is about what concept of hole. And you see for this also here E versus K diagram. E versus K diagram. This is related to this also. So this is my EK diagram near the top of the valence band, which is filled with electronic field state, which is filled with electronic. Okay, so this is my valence band, which is almost filled with electronic field state. Electronic field state. So these are electron, not hole. These are electron, not empty state. These are all electron. It is almost filled with electronic field state. Electronic field state. And these are what hole. Hole lies at the top of the near the top of the valence band. Okay, so these are what electronic field state. Conventional electronic field state. Conventional conventional electronic conventional electronic field state, conventional electronic field state, and these are empty state near the top of the valence band, near the top of the valence band. Okay, so this is in case of valence, but valence band, which is what valence band, which is almost filled with conventional electronic field state. Okay, so near the top of valence band there is empty state. Okay, so here if you see in case of what, in case of positively charged empty state. Okay, so which is occupying the original empty state. This will occupy the original empty state, and the other empty state are assumed to be empty or electrically neutral. Okay, so this is what somewhat this is new concept of positively charged empty state. Okay, so that we have seen through energy versus k diagram. Okay, energy versus k diagram. So this is all about this. Okay, so you can you can see this properly through these equations. Okay, so actually there is little bit confusion about that the movement of electron in the valence band, but it is actually the movement of hole. Okay, so movement of hole, because the electron is bound, so bound electron which is moving from one bound state to another bound state, but actual meaning is that the moving charge is what positively charged empty state. Okay, so which is giving what, which is giving current. Okay, so these are actually positively charged empty state which is moving in the valence band, and this is nothing but the movement of hole. Hole itself is nothing but it is a positively charged empty state. Okay, positively charged empty state. Okay, so which will give rise to what, current. It is the second important charge carrier for the semiconductor, which is responsible for what, current, which is responsible for current. Okay, so in general way we have seen, and this is the way to see this through energy versus k diagram. Okay, so this is all about the concept of hole, and next we will go for what, we will go for the effective mass of electron in the valence band, Okay, so this is all about this. Okay, so thank you.